In this section, Unit 3, Homework 3, we're going to be talking about functions and inverses of functions. So to get started, let's go ahead and review what a function is and how we determine whether an expression or a graph is a function. So the first thing we want to look at is testing for a function. Now we had several graphs that we looked at this in a previous section, but basically when we test for a function, we give a graph a vertical line test. Each value of x has a unique y. So for example, we could look at a couple different graphs here. And let's look at another one as well. Now for this first graph, notice that it passes that vertical line test. There's no point that it passes through. Each value of x has only one unique y. So this is a function. Now over here, it fails the vertical line test at several points. So for this value of x, there's two values of y, so this one is not a function. Well, that's the vertical line test. It tests for a function. Let's go ahead and just see if we can test to see whether a function has an inverse. So this is testing for an inverse. So if we talk about testing for an inverse, instead of the vertical line test, we're now using the horizontal line test. So let's go ahead and look at the same two graphs again, the one that we just looked at over here, and then our other one as well. So if we give this the horizontal line test, you can see that this value of y has three different x values. So this does not have an inverse because it fails the horizontal line test all sorts of different spots. This function, however, this graph, it's not a function, however, passes the horizontal line test, so this does have an inverse. Now sometimes I can't find the inverse, but if I know one exists, there's several characteristics of a function and its inverse. So the first thing we can do is we can look at a graph, give it the horizontal line test, and see if an inverse exists. If an inverse exists, then we can try and figure out what it is. And again, you can't always figure out what an inverse actually looks like. We can graph it, but we can't always find an equation or expression that models that. A couple characteristics about a function and its inverse. First of all, we have notation that we need to be concerned with. So to get started, f of x would represent my function. And then f inverse of x, and this is this little -1 in the exponent. This does not mean 1 over f of x. It does not mean to reciprocate anything because of the negative sign. This is notation that means the inverse of the function f. Okay, so our original function is f of x. The inverse of f of x is this notation, f inverse of x. And again, this does not mean 1 over f of x. This exponent does not mean to reciprocate. This is just the notation that represents the inverse. So that's important to remember. Now, another name for a function that has an inverse, we can come up here and talk about that, is called one-to-one. So these functions on the right-hand side that pass the horizontal line test would be called one-to-one. This one is not one-to-one because it didn't pass the horizontal line test. So what we have here, if a function f has an inverse, basically there's no horizontal line that intersects the graph at more than one point. Such a function that we were just looking at is called a one-to-one function. So if a function has an inverse, it is called one-to-one. Now another couple things that we can talk about. For f of x and f inverse of x, the domain and the range swap for these functions. So the domain of f becomes the range of the inverse and vice versa. So for f of x and f inverse of x, the domain and range swap. So the domain of f of x becomes the range of the inverse. Okay, also we could say the range of f of x becomes the domain then of the inverse. So the domain and the range swap. Okay, let's see what else we can talk about here. So if I had a function f of x and the function was made up of a set of ordered pairs, let's say -3, -1, 2, 7, 3, 6, and 4, 9, just making up some numbers here. The domain of f of x would be -3, 2, 3, and 4. So the domain of f of x be the set of numbers -3, 2, 3, and 4. The range of f of x would be the y values, the -1, 7, 6, and 9. Well, we can start talking about the inverse then. So my inverse function, the domain and the range swap. So these ordered pairs would swap. So this would become the ordered pair -1, -3, 7, 2, 3, 6 would become 6, 3, and 4, 9 would become 9, 4. So the domain and the range swap. So the domain of my inverse would be these values, -1, 7, 6, and 9. And then we could also talk about the range of the inverse would be these y values, -3, 2, 3, and 4. So again, this is an example of how the domain and the range swap. Now we're making a list of characteristics of a function and its inverse. So another thing that I could do is I could say, when I graph a function and its inverse, the two graphs reflect around the y = x line. So let's go ahead and take a look at what this means. I'm going to go ahead and pop in a Cartesian coordinate system so it's a little bit easier to see what's going on here. So to get started, when we're talking about a function and its inverse being symmetric across the y = x line, let's go ahead and sketch in that y = x line. Now this line goes through the origin, and then it goes through the point 1, 1, 2, 2, etc. Basically bisects the first and the third quadrants. So this line that we have drawn here is the y = x line. So let's go ahead and talk about two functions that are inverses of each other, and we won't establish that they're inverses. We're just going to look at them and decide, yes, they are inverses, and then look to see what the graphs look like. A little bit later on in the lesson today, we'll come up with a way that we can establish whether a function and another function are inverses of each other. So let's go ahead and look at this first line. This has a y-intercept of -1, So if it has a y-intercept of -1, that's the ordered pair 0, -1. Now this is just a straight line, so we're going to go ahead and graph the line. I want to choose a couple of ordered pairs. Let's go ahead and pick the point 2 for x. 2 times 2 is 4. 4 minus 1 is 3. So the point 2, 3 is also on this graph. So we go over 2 and up 3. So it'd be another point on the graph. We can also see that our slope is 2. So we'd rise 2, run 1, rise 2, run 1, rise 2, and we could run 1 again. You can see that these points line up very nicely. And we'll go down in this direction as well. So quite a few different ordered pairs here. Here's the point 3, 5. And then we went in the negative direction as well. And we have the point -1, -3. So those are ordered pairs. And for this line then, if I connect these, this is my function f of x. Now because it's symmetric about this line, every point on the blue line should reflect across this y equal x line. So what should happen here is this point should swap. So this should be -1, 0. So let's go ahead and see if that works. 1/2 times -1 is a -1/2. -1/2 plus 1/2 is 0. So that did work. These points did swap. So the point 0, -1 for our inverse becomes -1, 0. So you can see it reflects across that line. The point 2, 3 should come out as the point 3, 2 for our purple line. So 1, 2, 3, up 2. Now we can see that that point is reflective over here on the blue line. Let's go ahead and just do a few more of these. Let's look at 5, 3. So if we talk about 5 halves plus 1 halves would be 6 halves. 6 halves reduced would be 3. So that would be the ordered pair 5, 3. So 1, 2, 3, 4, 5, 1, 2, 3. And we can see that's the reflective point over here. And then this point 3, -1, again, is just a reflection of this, would be 3. 1, 2, 3, -1. Well, that one doesn't quite look right. Let's see what we have going on here. Okay, I see this one, and the blue line wasn't -1, 3, it was -1, -3. So there should be a negative sign here. That's this point. So when I swap them, that should be -3, -1, -2, -3, -1. So this had to have a negative sign in front of it up here. Then I can see it reflects across, and I can connect these points. Of course, drawn with the straight edge, these would be a little bit better, but you can see that each point on the blue line reflects to a point on the purple line, and they are mirror images across this y equal x line. They reflect across that line. So that's an example of when I plot a function in its inverse, what happens. A couple other characteristics of a function in its inverse. When I composite a function in its inverse, I should get x, and I have to check for f inverse of x and f inverse of f of x should both equal x. So what we could do here is we could talk about how do we verify a function and its inverse are actually function and inverse of each other. Now if a function has an inverse, it's a unique inverse. So let's keep a couple things in mind. We have some sort of a function, and we have its inverse. Okay? If I want to verify that they are actually inverses of each other, then what a common thing to do is to call this f inverse notation just g of x. But it has to be understood that it's f inverse of x. And it's really important that we understand that, because g of x could just be some other function. So what we can do is we can composite these. So f of g of x equals x if they're truly inverses. Also g of f of x would equal x. So this is what I do to verify their inverses. I composite them and if I get an x out of the expression, then that tells me that they're inverses. Now another way to think about composite, of course, is f of g of x. That means I take g of x and I plug it into f. Or I can check the other way and say, let's take f of x and plug it into g, and if I get x back out, that tells me that the function and the inverse that's listed are actually a function and inverse of each other. So we have to be really careful when we're checking to see and we're trying to verify to see if they're functions. You have to be careful about how you plug them in. So let's see, I think we've covered about everything. Oh, how to find an inverse. So let's say we do the horizontal line test and we verify that an inverse exists. How do we figure out what that is? Well, one answer is it's not always possible. The problems that we're going to be doing, if an inverse exists, we'll usually be able to find them. Okay, so to get started, we're usually given a function. Okay, and with this function, it's usually started off as y equal or f of x equal. So we're going to follow a series of steps. So the first step is, if you're given an inverse, let's say f of x equals something, replace f of x with y. Second step, swap the x and the y. And we'll see some examples of this as we get further into this assignment. The third step is we now solve for the new value of y from the swap value. And the fourth step then, the final step that we're going to be looking at here, is we are going to replace y, our value of y, with f inverse notation. Because that's to indicate that an inverse has been found. So those are all the characteristics of inverse functions. I think that we're definitely going to find some problems that we'll be working on a little bit later in this assignment to cover these. So this will be important to be able to flip back and forth too. Okay, so to get started, let's go ahead and determine whether a pair of functions are inverses or not. So determine if f of x equals 4x and g of x equals x over 4 are inverses of each other. So if you look up on our list, we're talking about composite notation, plugging one into the other and to see if you get an x back out. So to start, let's do f of g of x. So g of x is equal to x over 4. So I plug x over 4 in to my function in place of x. The 4's cancel and I get x, and that's what I want to get. I have to get this value of x. Now I also want to check the other direction, g of f of x. So my function is f of x, and I'm going to plug 4x, which is equal to f of x, into g. So again, g is equal to x over 4, but our value for x that we want to plug in is 4x. You can see that the 4's cancel, so we're left with x. So therefore, because when I composite these, I get x back either way, that tells me that f and g are inverses of each other. Now if I were to graph these, that would kind of help verify this as well. Now you have to be careful when you graph a function and its inverse. The scale on both the x and the y direction has to be the same, otherwise it will kind of distort the picture and it may not look symmetric around the y equal x line. So let's plot 4x and x over 4 on our same set of axes, and let's see what it looks like. So let's go to y equal, let's have 4x on one graph, the other graph x divided by 4, and let's check our window real quick. Notice I have negative 10 to 20, negative 10 to 20. I need to make sure that this is uniform on both sets of axes. Otherwise it won't look symmetric because of the scale. Okay, there's my first graph. Here's my second one. And it definitely does look like it's symmetric across the y equal x line. So let's go ahead and pop that into our lecture notes, and then we can sketch in the y equal x line. So this is not a way to verify that a function and another function are inverses of each other, but it's a way for me to look at the output from a graph and say that it's reasonable that they could be. So again, this is our y equal x line. It bisects that quadrant, and it's reflective about that line. So that makes sense that these would be symmetric. So my blue graph is f of x, and my other graph, g of x, is the red line. So function and its inverse. I've established that by compositing them or plugging one into the other. Now as you get working on these, sometimes they get a little bit more difficult when they're a fraction. But again, you just have to follow step by step. Make sure you use parentheses and follow through with your order of operations carefully. Now sometimes they give us some information to start with. So for this example, they tell us the function f of x equals x plus 7 is 1 to 1. And basically that means it has an inverse. So if a function is 1 to 1 and it has an inverse, they want us to find the inverse. So this is when we go through those 4 steps that we outlined above. Okay, so first step, we have f of x equals x plus 7. My first step was to replace y into the position of f of x. Second step, swap the x and the y. So x comes over here, y comes over here. I didn't solve, I just swapped these across. My next step is to solve for y. I would solve for y by subtracting 7 from both sides. So here, for my third step then, I'd have x minus 7 equals y. I'm going to rewrite this so the y is on the left. And then my fourth step would be to replace the y with f inverse notation. So what we've done here is we have found for the function f of x equal x plus 7, we've just determined that the inverse is equal to x minus 7. Now let's go ahead and see what this looks like graphically. And again, we're trying to graph x plus 7 and x minus 7. Let's go ahead and clear both of these. So x plus 7 and x minus 7. Now this should graph nicely because we already have that scale done from our last problem. Let's see if they reflect across this y equal x line. Should be parallel down, yep, there it is, parallel down here. So this one looks a little bit different. It doesn't cross in the middle like our last example, but we can see that it's symmetric about the y equal x line. So it's reasonable that the function that I was given and the function that I found are actually inverses of each other. Now once you find the inverse of a function, it is unique. That means it has exactly one inverse, so we just found it. So a function and its inverse are unique. And this is reflective across the line y equal x. So every point above is below and vice versa. The domain and the range swap. So that's an example of being given that a function is 1 to 1, asked to find the inverse. Now not all functions that you're given can you find the inverse for. It just kind of depends on the problem, but most of the ones that we're going to be looking at, in fact all of the ones that we're going to be looking at, is going to be possible. Now the example we just did was a pretty straightforward one. Let's go ahead and throw in one that's a little bit more difficult so when you run across it in the homework set, you'll have an example to follow. So find the inverse of the 1 to 1 function. And because we say 1 to 1, we know that it has an inverse, so we don't need to check. So, and let's go ahead and use f of x equals 8x plus 4 all over x minus 1. So we're going to follow those steps. Okay, first step. We are starting with our function f of x equals 8x plus 4 over x minus 1. First step means to replace the f of x with y. So I have y equal 8x plus 4 over x minus 1. Okay, so first step. Second step, swap the x and the y. So this value of y will become an x, and then all the values of y over here, or sorry, all the values of x over here will become a y. Okay, so that's our second step. Our third step is to now solve for y. Now this is not an easy step. There's a lot going on here with this problem. So to get started, I think what we'll do is we'll go ahead and clear the fraction by multiplying both sides through by y minus 1. And we're going to balance this equation. Whatever you do to one side, you do to the other. So what happens, the y minus 1's cancel over here. And over here, I'll distribute the x, and I'm left with xy minus x equals 8y plus 4. Now I want to move all the y's to the left, all the constants to the right. So let's go ahead and subtract 8y from both sides. And I have xy minus 8y minus x equal 4. Now x is not a constant, it's another variable, but it's not the variable that we want on the left. We want just y's on the left. So I go ahead and add the x across. And I have xy minus 8y equals 4 plus x. Now if you notice on the left, because we factored that y out, I have that greatest common factor. So I have y times the quantity x minus 8 equals 4 plus x. And then our final step in solving for y, where I divide both sides through by x minus 8. So these are pretty long problems. So I end up with y equal 4 plus x, or x plus 4, doesn't matter since I'm adding, over x minus 8. Last step, we go ahead and replace our value of y with f inverse of x. And that's my answer. So we can go ahead and actually graph these and see what happens. Now we have to be very, very careful that we're putting parentheses around the numerator and denominator. So let's go ahead and graph our original function. The original function was clear up here, 8x plus 4 over x minus 1. And again, we're just trying to see what these look like. So in parentheses, I want my 8x plus 4 divided by, and the denominator, let's use x minus 1. So that's my first graph. Now my second graph would be what we came up with for an inverse, and we have for an inverse x plus 4 over x minus 8. So in parentheses, x plus 4 divided by x minus 8. Okay, let's look at the graphs. Now remember, they should be reflective across the y equal x line. So I see that this graph should come up down here along the y equal x line. There it is, it's crossing. And then there's something else going on up here. It's a little bit hard to see, so let's go ahead and change our scale. Again, we have to be careful about our scale. We have to keep that consistent, otherwise it won't look like it's reflecting across that line. It'll look more squished than it should. So I'm going to change these from negative 20 to 20. Let's go ahead and have a look. We should get a little bit better look at what's going on in this top right hand quadrant now. Okay, so here's our cross right here, and then we should have another cross up here. So that does look like it reflects across the y equal x line. That's not a very good screen capture. That one's better. That other one had a lot of funny background to it. So from here we should be able to look at my function and its inverse. So again, this is reflecting across the y equal x line. So it does look reasonable that this is a function and its inverse. Now if I wanted to verify that for sure, I would just give it the horizontal line test. And again, I would just give the original function the horizontal line test. So just the blue graph or just the red graph is what I could do for these. Now remember, for a function and its inverse, the domain and the range swap. So you have to be careful about when you're working with these that you always keep that in mind. The domain and the range swap for a function and its inverse. So our next example, we're going to have a cubic root function. And we're going to do everything possible to this. We're going to find an inverse, we're going to graph it, and we're going to talk about the domain and the range. So let's go ahead and start with the function f of x equals the cubic root of x plus 8. Now notice the plus 8 is not underneath a radical sign. The first thing I want to do is find the inverse. So we want to find the inverse of x, f inverse of x. So first step, replace f of x with y. So I have y equal x to the 1/3 plus 8. So cubic root is the same as an exponent of 1/3. Okay, second step, we're going to swap the x and the y. So I have x equal y to the 1/3 plus 8. Third step, go ahead and solve for y. So I'd subtract 8 from both sides. And I end up with y to the 1/3 equals x minus 8. And then we would cube both sides. Now the reason we cube both sides is 1/3 times 3 is 1. So on the left hand side I just get y equal x minus 8 to the 3rd. Our fourth step would then to replace the value of y with f inverse of x, x minus 8 cubed. So that's an example of finding the inverse. Second, we want to go ahead and they ask us to choose a graph that has the function and its inverse listed. Well, what you want to do here is to actually go through and graph these. You can either do this with ordered pairs or just grab your graphing calculator to help you out here. So our first function was the cubic root of x plus 8. So that would be x to the 1/3. And make sure you have your exponent in parentheses if you don't have your exponent key. And that's plus 8. And then my other function that we just found for my inverse was x minus 8 has to be in parentheses to the 3rd power. So let's go ahead and graph these and see what it looks like. We might have to change our scale, but we should be able to get a pretty good picture. So there is the first function, f of x, and then it should reflect around the y equal x line. And it looks like it does. So let's go ahead and take a screenshot of that piece and then talk about how we can choose the correct graph given in my math lab. So what we have here is my f of x function. So this is f of x equals the cubic root of x plus 8. The red is my inverse. This is f inverse of x equals x minus 8 quantity cubed. Now notice these are reflective about the y equal x line that bisects the first and third quadrants. So you should be able to look at the graphs that they're given and see which one matches that best. Now next thing they want us to do is to state the domain and the range of each function. Well, remember, there's no restrictions here. It's not a square root, it's a cubic root. I can plug in anything I want. So if I look at the red graph or the blue graph, we can see that they cover all real numbers. So for here, I think this is part C, the domain of my function f is equal to the range of my inverse. And they're both equal to all real numbers from negative to positive infinity. Now the same will hold true for the range of f of x being the same as the domain of the inverse. And in this case, it's all real numbers, negative to positive infinity. So these are not all that interesting because they're all real numbers, but some graphs you will get something a little bit different for. Okay, to wrap up this particular homework set, I want to go back through and talk about composite functions very quickly, and then we'll talk about composite functions, not just with an f and a g, but let's say an f and a g and an h, three things combined. So let's go ahead and look at some of the homework problems you might run into. So again, we're looking at composite functions. So these are a bit of a review. So we're given two composite functions, an f of x and a g of x. Now what they want us to do is they want us to take 0 and plug it into my function g, so that's my first step. So I'd have 8 times 0 minus 1. 8 times 0 is 0. 0 minus 1 is a negative 1. So then I take this value of negative 1 and I plug it back into my function f. So that would be 5 times a negative 1 minus 1. Negative 5 minus 1 is negative 6 then. So what we do when we have these composite functions is we plug one into the other, and then once I get one solution, I go ahead and plug it into the next one. So for this simplification, my final solution is negative 6. The negative 1 is an intermediate value I use to find the actual value. Okay, let's look at another example that you'll see in this section as well. In this one, we're going to be using the inverse notation, so it was going to look a little bit different. Okay, so for this one, let's go ahead and read through it. It says, let the function f be given by this equation, f of x equals 5x minus 2, and it says evaluate f inverse of 3 without finding an equation for the function. So they want to know what f inverse of 3 is. Now we have to remember the business about the domain and the range swapping. So this value of 3 is the domain of the inverse. The domain of the inverse, remember, is the range of my original function. So this is the information that we're going to use here. So my original function, f of x equals 5x minus 2, the range would be the y value. So I replace the f of x with y, and then since this is the range of my original, I plug that in for y. So I get y equal 5x minus 2. And then I go ahead and solve for x. So I'd add 2 to both sides, divide both sides through by 5, and I get x is equal to 1. So f inverse of 3 is equal to 1. This value of 1 is the domain of f of x, which means it is the range or the output of f inverse of x. So it's a little bit tricky. You need to remember to swap those around when you're working this problem. And when you swap those, remember the domain and the range swap, it helps you to find the functional and the inverse value without actually plugging in and knowing what the inverse was. Okay, last problem. For this problem, instead of just being given a function and its inverse, like f and g, we're going to be given 3 functions. And these are actually pretty easy to work with. As usual, we follow the same set of rules. We plug into the first function, and then to the second and to the third. We have to make sure we do it in the correct order though. If we do these in the wrong order, I will get the wrong answer. So let's go ahead and start with our notation here, g of f of h of 0. So let's go ahead and start with h of 0. So I'd have 0 squared plus 3 times 0 plus 4. Because I plug this in for h. So when I get my solution here, I have 0 plus 0 plus 4. So I get h of 0 equals 4. Okay, so this piece right here is equal to 4. So I have g of f, h of 0 was 4. So my next step is to take 4 and plug it into f. So f of 4, I would plug in up here. I'd have 4 times 4 minus 1. 16 minus 1 is 15. Okay, so now I know f of 4 is 15. So now I take the value of 15 and plug it into g. So again, it's important that you do these in the correct order. You don't do them alphabetically, you do them as the order given. You do working on the inside, so I'd plug it into h, get my answer, plug it into f, get my answer, plug that answer into g. So here I have 2 times 15 minus 1 2 times 15 is 30. 30 minus 1 is 29. So again, order matters here. You have to be really careful that you run through these in the correct order. If you have any questions while you're working, please bring your questions to class. We'd be happy to go through any of the questions that you have during the lecture. You can also stop by the Math Center or my office. Good luck.